Welcome to ES 310 Lesson 23. Today we'll be moving on into the kinetics of rigid body motion and focusing in on translation of those rigid bodies. We will be using the kinematics that we've learned in the last few lessons in order to apply Newton's second laws to rigid bodies to determine the forces that are causing those changes in velocity and acceleration. We will also introduce the concept of kinetic moments to simplify analysis in certain situations. More information about these topics can be found in Hibbler's Dynamics textbook, Chapter 17, Sections 2 and 3. In the grand scheme of things, we have now covered all of the particle analysis that we are planning on looking at. So we started with kinematics, looking at translation, because particles only translate, they do not rotate. And then we looked at kinetics, and we looked at Newton's second law, work energy, and impulse momentum. In the last few lessons, we've been looking at rigid bodies, which translate and rotate. And we've looked at the kinematics of that translation and rotation. And now, for the first time, we are moving into the kinetics. We'll be looking at Newton's second law, and today we'll be focusing on the translation of rigid bodies using Newton's second law. So, just as a reminder, rigid body translation means that a line on the body will translate but will not rotate. So those lines always stay parallel, but they may move along a straight line or along a curve. If we remember back to using Newton's second law for particles, we used F is equal to ma in the x and y direction. We're going to do the same thing here, except now we have a collection of particles, which is a really rigid body. And so we will say that the sum of all of the forces is equal to the mass times the acceleration in the x and y directions of the center of mass. And it's very important to realize that this is of the center of mass, not of any arbitrary point on the body. It has to be of the center of mass. Since we have translation, we do not have any rotation. So we're looking purely at translation. And so the sum of the moments is going to be equal to 0. But those are moments around the center of mass, once again. So we have to remember, always around the center of mass is going to be equal to 0. If the object is moving on a curved path, it can still be translating because a line on that object may not be rotating. We would then use the normal tangential components, and we'd have the forces in the normal directions equal to mass times the acceleration of gravity in the normal direction. And the forces in the tangential is equal to mass times the acceleration of the center of gravity in the tangential direction. And once again, the moments around the center of gravity is equal to 0. Since we're dealing with moments, let's take a moment to review that. We saw moments in statics. Remember, definition of a moment is the tendency for a body to rotate around a point that is not on the line of action of the force. And so, if we apply a force to a body, and it is some distance r from the point of interest, it may cause that body to rotate. So in vector math, the moment is the cross product of r and f, which can also be written as r times f times the sine of theta. And it is in the k-hat direction. It's usually pointing perpendicular to the plane of motion. There are several different possible ways of finding this moment. We can use this vector notation, so write out r in ij and k hat components, write out f in ij k hat components, and take that cross product. We can also find the part of r that is perpendicular to f and multiply them together, or we can find the part of f perpendicular to r, multiply them together, or we can find the angle theta that's between r and f and use the r times f sine theta. Depends on the problem and on your preference of how you might find these. The directions, remember, use your right-hand rule. Counterclockwise is positive, clockwise is negative. The process for solving these problems starts with us drawing a free body diagram. We then establish an inertial reference frame where the acceleration of the reference frame is 0, and then we draw forces as components along the coordinate directions, which makes finding xy components of things easy. We write our equations of motion, which state that the sum of forces in the x is equal to mass times the x acceleration of the center of gravity. Sum of forces in the y is equal to m times the y part of the acceleration of gravity. And the sum of the moments around the center of gravity is equal to 0. And we use kinematics if necessary to determine velocities and positions if they are requested in a problem. Remember, we can also use normal and tangential components if we're moving along a curved path. So let's take an example of this. We have a man pushing on a cabinet. The cabinet weighs 150 pounds, so there is a weight acting at the center of gravity of 150 pounds, acting straight down. There are more normal reactions under the legs, so we have a normal reaction NA, and we've got a normal reaction NB. And if the man weren't pushing on this, those two would be equal, both equal to half of the weight. But since the man is pushing on it, NB is going to be bigger than NA. More of the 150 is going to be held by NB than NA. There are two coefficients of friction that they give us. The coefficient of static friction is 0.2 and the coefficient of kinetic friction is 0.15. And we need to figure out what the acceleration of this cabinet is and how much, and the magnitudes of the two normal forces. So there's friction on the feet, which will be acting in this direction, and we've got FB, FA. So there are three possibilities for the motion here. And this is one of these cases where we're going to guess one of them, test the other two, and hope we guess right. So one possibility is that no, it's not moving, it's still. If it's still, it would be still because the P that he's pushing with is less than the static coefficient of friction times the normal force, or the static friction. In this case, the normal force would be NA plus NB, which is the total weight. So this would be 0.2 times 150. So if the force he pushes with is less than 0.2 times 150, the cabinet doesn't move. The second possibility is that it slips. If it slips, then that P is going to be bigger than the coefficient of static friction, and the friction is going to be equal to mu times N for each case. So FA would be mu times NA, FB would be mu times NB. If it tips, then we have that NA would be equal to 0. Right? So if NA turns out to be negative or equal to 0, then this thing would be tipping, because this foot would be lifting off the ground as it tips. So let's guess. I'm going to guess that it's going to slip, and then we'll come back and we'll test the other two possibilities. So if it's going to slip, looking at our free body diagram, we have some equations. We have that the sum of forces in the x direction is equal to P, which we know, minus the two frictions, FA minus FB. So the frictions can be clumped together, and we have P minus, friction is mu K times N, according to this definition. So mu K times NA plus NB. And this is equal to the mass times the acceleration of the center of gravity in the x direction. Alright, now let's look at the y direction. Force in the y direction is equal to the weight, which is pointing down, so on negative 150, plus NA plus NB. That is going to equal 0 because it's not accelerating in the y direction. So this tells us that NA plus NB is equal to 150. So we can take this 150 and plug it in up here, and we can get that the acceleration in the x direction of the center of mass is P, which was 35, minus 0.15 times 150. Gives us mass times acceleration of the center of gravity in the x direction, which gives us then that the acceleration of the center of gravity in the x direction is equal to 2.68 feet per second. Okay, now we need to figure out if what is NA and what is NB, because they're not equal. So this requires a moment. Now the moment equation we have is that the sum of the moments around the center of gravity is equal to 0. Now in statics, where nothing was rotating, nothing was moving at all, we could pick any point we wanted for the center of gravity to sum our moments. And so we'd usually pick one of the feet where we have a lot of unknowns, and then from that be able to find the other unknowns. But in this case, we have to pick the center of gravity, so that makes it for a more complicated equation, but we can write it out. We have center of gravity, so let's see, P is causing a negative moment, right? Because it's causing this to move clockwise around G. So negative P times the distance, the perpendicular distance between P and G would be 3.4 minus 3.5, which is 0.5. So that's the moment due to P. Then we have the moment due to NA. NA is also causing a negative moment, NA, and the perpendicular distance from G to NA would be this distance right here, which is 1. Then we have NB, which is giving us a positive moment because it's causing it to move counterclockwise, and also at a distance of 1. And then we have the two frictions. So we have FA, which is giving us a negative moment, FA times the perpendicular distance from FA to G would be this one, so 3.5. And then we have FB, same distance and same direction. So that sum is equal to 0. We know P, we don't know NA, we don't know NB, but we do know FA and FB in terms of NA and NB, so this really is two unknowns, and when we can use this equation up here as our second, and we can find NA and NB. So the P goes to the other side. FA is mu K NA. FB is mu K NB. We can combine things together. We get negative 1 minus 1.15 times 3.5 times NA plus 1 minus 0.15 times 3.5 times NB is equal to P, which is 35, times 0.5 on the other side, which is equal to 17.5. Now we have two equations, two unknowns. You can use your calculators to solve. This is equation 1, this is equation 2. You can use your calculators or various other means. We get that NA is equal to 26.875, and we get that NB is equal to 123.125. So now we have to go back to our possibilities and make sure that we actually guessed correctly. So based on the fact that NA is greater than 0, we know that it doesn't tip. No tip. So we know that it was not this one. Now we need to check here. Is P less than mu s times n? Well, mu s times n is 0.2 times 150, which is 22.5, which is not greater than 35. So no, not true. So we did in fact guess correctly, and this does slip. Now we were sort of hindered in that last problem. It was more complicated than needed, because we had to solve moments around our center of gravity. There is a way that we can sum moments around any point, and that is using kinetic moments. Now, a key point here is kinetic moments are non-physical quantities, all right? So don't get them confused with real moments that are caused by real forces. These are moments, in some sense, that are caused by the lump sum of the forces that we know are there because they're causing accelerations. All right, so just like we can write that F is equal to ma, So there's a force and there's a mass times an acceleration because there's that force, right? ma can't be really called a force. But what we're going to do is take the moment of ma. So we're going to do r crossed with ma to find these kinetic moments. They're called kinetic moments because they're dealing with our accelerations. So kinetic moments, again, not real moments. They have this cursive m type notation. And they're equal to, so the mass times the acceleration of the center of gravity in the x direction times y, which is the perpendicular distance, right? And plus mass times the acceleration of the center of gravity in the y direction times x, again the perpendicular distance. And then we have this I, so this is the moment of inertia, ig times alpha. Since it's not rotating, for now we're going to ignore this. And we'll talk about these moments of inertia in the next lesson. But so for the purposes of translation, we just have these first two. The signs come from the direction of those motions. So if you draw the fake force, that is the ma, and then we can figure out the directions the same way as you normally do. So once we know these kinetic moments, we can sum moments around any point P, because the sum of the moments around any point is equal to the sum of the kinetic moments around that point. And these are very useful in problems with multiple centers of masses, so we have like two bodies. But can also be useful in problems like the last one, where we could now solve for sum of moments around one of the feet and have only one unknown in our equation. So let's take an example where we will use these kinetic moments. We have a man on a bicycle. We're given, this is one where we have two center of masses. So we've got the center of mass of the man up here. We've got the center mass of the bicycle right here. We're given the mass of the bicycle is 40, and we've given the mass of the man is 60. There's a brake, and it's applied to the front wheel, and that causes the bike to decelerate at a constant rate of 3. So the acceleration is going to be in this direction with 3 meters per second squared, right? Assuming that the velocity is in that direction. Let's identify some positive directions. This is the I hat and the J hats, positive directions. All right, so that force that caused that deceleration acted on the front wheel. So if it's going to cause an acceleration or a deceleration in the positive I hat direction, it's going to also point in the positive I hat direction. So that's that F. And we also have a normal force on the front wheel and a normal force on the back wheel. So that then completes our free body diagram. So now we can write our equations of motion. So we have, in the x direction, not very helpful, but we have this force F equal to mass times the acceleration. All right, then we have in the y direction, we have, let's see, the weight of the man going down, the weight of the bicycle going down, plus NA going up, plus NB going up is equal to 0 because there's no acceleration in the y direction. Now we have moments. Now we can't just sum moments and set it equal to 0 because we have two center of masses. So we'd have to split the bodies up in order to do that. But we can use these kinetic moments. So we're going to pick a point. I'd say let's pick point A, because there's two unknown forces acting at point A. So moments around point A are equal to these kinetic moments. Let's make a cursive M. Kinetic moments around point A. So, the moments around point A, let's look at point A. We've got the weight of the man, or the weight of the bicycle, times the distance from A to where that weight acts is 0.4. And that is a negative moment. Minus the weight of the man, also going to be a negative moment, times the distance to where that acts is 0.6. Plus the NB, the positive moment times 1 is the distance. So those are all the forces that cause a moment around point A. On the other side, we have the kinetic moments. So we've got, I'm going to draw them as dotted lines. The man and the bicycle are both decelerating or accelerating in this to the right. This is going to be m of the man times 3, and this is going to be m of the bicycle times 3. So those are our fake forces that we're going to need to use in the moment equation. So we've got mb times the distance to mb, perpendicular, is 0.4, and that is a negative moment. So minus mb times 3 times 0.4. And the same with the man. We've got minus, and that one's 1.25 times times 3. So those are our three equations. This one is not so useful, but using these two, we should be able to find all of the things we're interested in, which in our case is NA and NB. So the only unknown here is NB in this bottom equation, so we can solve for NB, and that's equal to 237.12. Then take MB, plug it in up here. We know the weight of the man and the weight of the bicycle, so we can find that NA is equal to 743.88. The other way that we could have solved this problem without using these kinetic moments would be to draw it as two free body diagrams. The free body diagram of the man, the free body diagram of the bike, and work through it that way. But this simplifies things tremendously. Just remember, these are not real moments. These are kinetic moments.